Good morning. I am Prasannanjaneya Reddy, working as Assistant Professor in the Department of ECE, IARE, Dundigal, Hyderabad. In this session, we are going to discuss about embedded system architecture. So, first, what is an embedded system? Once again, revise this definition. Embedded system is defined as embedded the firmware into hardware to do specific one or few highly focused jobs, often with real-time constraints. Example, mobile phones. So here we are adding intelligence to the hardware for doing specific functions. This hardware contains various hardware components. We will check one by one on their functionality. First, the basic element of the embedded system is core component. Means which executes the instructions. Core components are used to process the instructions or executing the instructions. Examples: microprocessors, microcontrollers, digital signal processors, are programmable logic devices like programmable logic array, programmable array logic, or complex programmable logic devices, or field programmable gate arrays, or application specific integrated circuits, or programmable system on chip, or commercial off the shelf components. We may use any one or few of these components for processing our design or instructions. Okay. Core components are used to executing the instructions. Second, we need to store the instructions. For that, we require memory devices. Memory devices store the information. Here, two types of memories are there: primary memory, secondary memory. Why we call primary memory, not secondary or third? Means whenever we are doing the operations or while doing the operations or task, the processing element accesses the information from primary devices. That accessing speed is more when comparing with accessing from the secondary memory devices. That's why we are calling primary. These primary memory devices are also called volatile memory. Volatile means whenever the power is turned off, the data will be erased. The type of memory called volatile memories. Examples for volatile memories are static random access memory or dynamic random access memory or ferroelectric random access memory. We may use any one or few of these memory devices for doing our job. Another one is secondary memory devices. Even the power is turned off, the data is not erased, like our memory cards or hard disks. Next, input devices. So, for continuously capture the current information, if any unknown person comes near to the door or not, or what is the heartbeat of the patient, that needs to be monitored continuously. At that time, we need to get the corresponding parameter value. So, by using input devices, we can continuously get the current data. So, there are various types of input devices are there. And first is sensor. Sensor is a transducer which converts the physical information into the electronic signal. So there are various types of sensors are there: temperature sensor, pressure sensor, or humidity sensor, proximity sensor. Like that, various types of sensors are there. We may use different types of sensors based on the requirement, or we can use input switches and various types of devices. Next, output devices. For monitoring and controlling the parameters, we require the output devices like digital dashboards, like LCD display, CRT display, LED display, or actuators mainly. Actuator is a transducer which convert the electronic signal into physical changes like speakers. Next, additional hardware means for doing special functions like our information is analog in nature, but the processing elements process the digital information. So at that time we need to convert the analog information into the digital. For that we require analog to digital converter. Okay, analog to digital converter. At the same time, after completion of operation, the information is digital in nature. Again, that is needs to be converting into the analog in nature. For that, we require digital to analog converter. Okay. Similarly, real-time clock for providing the timing reference, interrupts for doing the required desired job instantly, or debuggers, or watchdog timers. Like that, we are using different types of special hardware or additional hardware circuits for doing corresponding operations. Based on the requirement, we may use any of them. Next, for sharing information among all these devices, we require communication interfaces. Communication means sharing the information between all these peripherals. This firmware. Okay. So like this, this embedded system is divided into 6 parts. First one is core components for executing the instructions, or firmware. Firmware means some set of instructions. And memory devices for storing the instructions. Input devices for capturing the current data. And output devices for monitoring and controlling the devices. And additional hardware for doing the special functions. And communication interfaces for sharing the information among all these things. We will check one by one in detail. Okay. First, I am saying core components. Core components, what it will do? It will execute the instructions. Execute the instructions. Okay. Examples for core components are either microprocessors we can use, or microcontrollers we can use, digital signal processors, or we check one by one. First, microprocessors. What is microprocessor? Microprocessor is a single silicon chip that represents central processing unit like CPU. Central processing unit. It contains arithmetic and logical unit, control unit, and working registers. It performs arithmetic and logical operations and control operations. Example for CPU or microprocessor is 8086. In the beginning days, we are using Intel. They designed the 4004. Later on, 4040. Next, 8008. Next, 8080. Next, 8085. Next, 8086. And 80286. 80386. 80486. Next, dual core. Next, quad core. Next, octa core. Next, hexa core. Next, core i3. Next, i5, i7, i9. Like this, various processing elements are there. As the technology advances, we are adding more logic density in a single chip and providing more number of features as per the customer requirement. We may use any one of them for designing our requirements. So this is design manufactured by the Intel company. At the same time, different vendors coming to the market, they are designing various types of processing elements. Some of the manufacturers are Atmel, AMD, Qualcomm, Texas Instruments, NXP Semiconductor, Philips. So and so on. So the competition increases. So we are getting advanced processing elements for designing our requirements. We may use any one of them. Okay. We'll check one processing element thoroughly. That is 8086 microprocessor. So we are saying microprocessor is a single silicon chip that represents central processing unit. Okay. It performs arithmetic and logical operations and control operations. It contains working registers. So first see the features. It is a 16-bit microprocessor. It contains 16 data lines and 20 address lines. So since it contains 20 address lines, it providing a 2 power 20 addresses means it interfaces up to 1 megabyte memory. 1 megabyte memory. Next, it contains 14 16-bit registers. 14 16-bit registers. Those are general purpose registers like AX, BX, CX, DX. Segment registers, code segment, data segment, stack segment, extra segment. Pointers, instruction pointer, base pointer, stack pointer, and index registers, source index, destination index, and flag register. These are the 14 16-bit registers. Next, it provides 3 different clock frequencies, that is 5 MHz clock frequency, 8 MHz clock frequency, 10 MHz clock frequency. So it is operated in minimum mode and maximum mode. Means whenever 8086 do the operations by itself, like arithmetic and logical, whatever may be, the operation is performed by 8086 itself. That at that time, that 8086 is operated in minimum mode. Sometimes 8086 is not possible to do some of the operations like floating point operations. At that time, 8086 needs to be interfacing with the external processing elements like 8087 for doing the floating point operations. At that time, that is interfacing with 8087, the type of operation is called maximum mode operation. Next, it provides pipelining technique like fetch, decode, execute. So what is the advantage of pipelining technique? Suppose if I want to perform, I want to add two numbers, 1 plus 2 equal to 3. For that, I need to write the instructions, write the program. So here I am writing the assembly level language, move AX comma 1, move BX comma 2, add AX comma BX, INT 03. So in this case, if I am doing the without pipelining means first fetch the instruction, decode the instruction, execute the instructions. Like that for all these 4 instructions, it requires 12 clock cycles. Suppose each operation taking 1 clock cycle, decoding take 1 clock cycle, executing take 1 clock cycle, like that. For doing this operation, 1 plus 2 equal to 3, addition operation, I require 12 clock cycles. So without pipelining, it takes 12 clock cycles, means that takes much time. So with pipelining, first fetch, decode, execute. This is the first instruction, second instruction, third instruction, fourth instruction. In the first clock cycle, I am fetching the first instruction. In the second clock cycle, I am decoding first instruction, at the same time fetch the second instruction. In the third clock cycle, executing the first instruction, decoding the second instruction, fetching the third instruction. In the fourth clock cycle, executing the second instruction, decoding third instruction, fetching fourth instruction. Fifth clock cycle, in the same manner, similar procedure. So finally, for doing this operation, I require 6 clock cycles by using pipelining technique. Without pipelining technique, I require 12 clock cycles. So as the number of clock cycles reducing here, we are reducing the number of 12 clock cycles to 6 clock cycles. What happens as the number of clock cycles reduces means execution time reduces. Execution time reducing means speed is increases. Okay, so 8086 supports the pipelining, 3-stage pipelining technique. First stage, second stage, third stage. So it supports 3-stage pipelining technique. Next, it provides 33% duty cycle. Means the on time is 33%. Clock signal is on time is, this is 33%, remaining 67%. If you look at any clock signal. This is period, time period T. So it is available in 40 pin ceramic dual inline package. 8086 microprocessor is available in 40 pin ceramic dual inline package. Okay, these are the features. So by use what I am saying, 8086 do the arithmetic operations and logical operations and control operations. We will check its architecture. First, like I am considering this is memory. This is bus. Here I am taking arithmetic and logical unit, adder, adding unit. For this I am taking some registers, code segment, data segment, stack segment, extra segment. Here I am taking instruction pointer. So from these registers, I am taking offset address from instruction pointer and segment address from code segment. Finally, segment address into 10 plus offset address, that indicating 20-bit physical address. So by using this 20-bit address, I am accessing that corresponding memory locations. So I am going to the memory, access that memory location. From that memory location, I am fetching the instruction that is stored in the instruction queue. So instruction queue size is 6 bytes. Okay. First, I am getting the offset address from the instruction pointer and segment address from the segment register, and calculating segment address into 10 plus offset address. I am getting 20-bit physical address. So I am going to that memory location and access the instruction from that memory location. Then that is copied into the instruction queue. So 8086 prefetch the instructions up to 6 bytes. 6 bytes instructions. So prefetching the advantage is no need to waiting for accessing that information. So accessing time is reducing means automatically speed is increases. This is one of the benefit. Then that is giving to the, that is decoded, that is decoded. The instruction is decoded. After decoding that one, based on the operation, either arithmetic logical operations or control operations, based on that, that is giving to the corresponding control unit. This is arithmetic and logical unit. This is timing and control unit. So based on the instruction, it goes to the corresponding unit and do corresponding operations. Now, while doing the operations, it requires the information. I require 1 and 2. So that is taking from the corresponding registers. In the previous instruction, AX, BX, CX, DX are base pointer, stack pointer, source index, destination index. Okay. Okay. So while doing this, either arithmetic and logical operations or control operations, based on the operation, it will access the information from the corresponding registers and do the operations. After completion of operation, the flag register, again it contains one more register, that is flag, that means status register. Either carry is generated or overflow occurs or result is 0 or any interrupt occurs. All these things will be the status information is available in the flag registers. Like that, the microprocessor 8086 will do the arithmetic and logical operations and control operations. So first, microprocessor. What is microprocessor? Microprocessor is a single silicon chip that represents central processing unit. It performs arithmetic and logical operations and control operations. Okay. Example 8086 microprocessor. If you look at this architecture, it performs arithmetic and logical operations and control operations logically. Next, coming to the microcontroller. Already 8086 is discussed in the previous session. Now we are going to discuss about 8051 architecture. So The advantage of the 8086 is providing maximum performance. But the limitations for 8086 is, if you want to design particular embedded system, it requires the memory for storing the instructions, input and output peripherals for interacting with external world, special hardware for doing special functions, and communication peripherals for sharing the information among all these things. These are not available within the chip. These are not available within the chip. Okay. So we need to purchase separately and interfacing with 8086 externally. So the automatically what happens is, whatever the power consumed by these elements will be increases, and the cost of the components increases. Whatever the cost of the components, the cost will be add extra more. Size increases, whatever the space occupied by those components, when comparing with microcontroller based design. When comparing with microcontroller based design, and whatever the power consumed by those extra components, the power consumption increases and power dissipation increases. So we need to we require external cooling components, cooling fans or ACs to provide the cooling to the devices. So all these things will be increases, speed reduces, cost increases, size increases. Okay, to overcome these limitations, we need to go to the microcontroller. So what is microcontroller? Microcontroller also is single silicon chip that represents central processing unit, and it contains memory, input and output peripherals, and special hardware and communication peripherals within the chip, within the silicon chip. Okay. So one of the example for microcontroller is 8051. Okay. One of the example for microcontroller is 8051 microcontroller. If you look at this microcontroller architecture, first it contains CPU for executing the instructions. Next, memory. So on chip RAM, that is 128 bytes on chip RAM, and 128 bytes special function registers. 128 bytes for special function registers within the chip, and it contains 4 kilobytes on chip ROM for storing the instructions, and it contains 32 IO pins, like each like these are the port 0 to port 3, like this is port 0, port 1, port 2, port 3. Okay, each port contains 8 IO pins. Totally 32 IO pins it contains for interacting with the external world, and it contains two 16-bit timers, timer 0 and timer 1. 16-bit timer, at 16-bit indicating at a time it will access the 16-bit information. Next, it contains 6 interrupts. Those are timer 0 interrupt, timer 1 interrupt, or INT external interrupts 0 and 1, EX0, EX1, external interrupt 0, external interrupt 1, timer 0, timer 1 interrupts, and serial port interrupts, transmitting interrupt, receiving interrupt. Totally 6 on-chip interrupts are there. Next, it contains on-chip clock oscillator unit. Okay, and it contains UART. Okay, it contains UART for sharing the information among all these peripherals. Okay, so all these are contains within the chip. So what is the advantage? If I want to design particular embedded system, at that time I require all these elements. If I use 8086 processing elements, these elements are used separately externally from the 8086 chip. So the cost increases, whatever the cost of these components, and size increases whatever the size of these components, and cooling fans required, power consumption increases whatever the power consumed by these external elements. All these things will be increases. Okay, so by if I am using 8051 means, so we can reduce when comparing with 8086 based design. Okay. So differentiate microprocessor and microcontroller. How we can differentiate? This is initially we are using microprocessors for designing the embedded systems. Later on we are using microcontrollers. If you look at the microprocessor, it is CPU. It is CPU. It contains arithmetic and logical unit, control unit, working registers. If you look at the microcontroller, it contains CPU. Along with CPU, it contains memory for storing the instructions, and it contains input devices for capturing the information, output devices for monitoring and controlling. Okay. And special hardware means additional hardware like timers, counters, or on-chip debuggers like this, and communication peripherals for sharing the information. Communication peripherals for sharing the information among all these things. Okay. So microprocessor is a single silicon chip that represents CPU. It contains arithmetic and logical unit, control unit, and working registers. Okay. It performs arithmetic and logical operations, control operations. If you look at the microcontroller, it is also a single silicon chip that contains on-chip CPU, memory, input and output devices, additional hardware, and communication peripherals within the chip. Within the chip. This is the first difference. Second, microprocessor based embedded system design requires external components like external memory, external IO peripherals, external hardware, external communication peripherals. Whereas microcontroller based design, mostly it contains within the chip. If it is not sufficient, then only we can go for externally. Mostly all these are available within the chip, so no need to purchase the external components. Since we are using external components, the cost increases. Cost is more, size is more, power consumption is more. Power consumption is more, and since it needs to access externally, the accessing time increases. Accessing time. Automatically, it leads to reduce the speed in microprocessor based design when comparing with microcontroller based design. So all these are eliminated here. So example for microprocessor is 8086 microprocessor. Example for microcontroller is 8051 microcontroller. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.